Hello and welcome to class 14 on correlations. I've got a few basic points that I want to make in this video, and then we've got some exercises. Some of them were taken from the Southworth and Swire textbook, and some of them are just things that I made up. But the basic topic here is correlations, and I just have a few points I want to make about correlations. Correlations are comparative. When we say two things are correlated, we are actually making two separate quantified categorical statements and comparing them. And we can also set up a kind of diagram that allows us very simply to represent them, and we're just calling those correlation diagrams. The other basic point is that correlation is not causation. Correlation happens when two things co-occur. They occur together all the time. But just because they occur together all the time doesn't mean that one is causing the other. So, a few basic lessons about correlation and causation. Correlation is not causation because correlation is symmetrical and causation is not. Correlation lets you predict. If you know two things are correlated, you can make some judgments about the future. Causation lets you change. Causation lets you affect the future. Now, you may not have understood those summary points that well, but after I go through them in more detail, hopefully you will get a better sense of them. So let's start with just the idea that a correlation is comparative. What is a correlation? A correlation is a relationship between two variables that measures how closely they are related. Now, remember when we are talking about generalizations, we are using some terminology from statistics. So we talk about populations and samples. And the population is just a big group of things, any kind of thing that you want to make an inference about. And the sample is the smaller portion of the population that you can actually study, right? So whenever you make an inductive generalization, you move from a sample to a population. When we talk about inductive generalizations, we talk about and populations and samples. We describe them in terms of variables and values. So a variable is going to be a property of the individuals in this population that can take many forms, and the values of the different forms that property can take. So one standard example that we talk about all the time in statistics classes is the idea of pulling balls at random out of an urn, right? And I always picture a big coffee urn like you would have at a, like the coffee shop. And you can imagine that the balls in this urn have two different colors. They could be red or green. So color is the variable, red and green are the value. You might also say some balls are large and some balls are small. So size would be the variable, and large and small are the values. So let me take an example from Southworth and Swire to kind of make this more concrete. Standard example: smoking correlates with heart attacks. So we can imagine that we have two categorical statements, quantified categorical statements. 30% of smokers will have a heart attack, 20% of non-smokers will have a heart attack. So our variables are smoking and heart attack, and our values are yes and no in each case. We can use these two quantified categorical statements to create a diagram that has 4 quadrants of varying sizes here. So here is an example of a correlation diagram. You can imagine you've got 2 columns. One is the column of smokers and one is the column of non-smokers. And imagine that 30% of the smokers have heart attacks and 20% of the non-smokers have heart attacks. That means that smoking and heart attacks are correlated. Smoking and smokers are, you can predict that they are more likely to have a heart attack. Now, I should emphasize that Southworth and Swire emphasized that they were just making up numbers for this example. And quick Googling tells me that 3.1% of Americans over 20 have had a heart attack. So it seems to me that the numbers in this example are really high. But it doesn't matter that these are all made-up examples. Although smoking really does correlate with heart attacks. So with these diagrams, you've got, you're going to have a correlation whenever the 2 bars are different sizes. So let's go back to our example of red and green balls in an urn. Suppose the red balls tend to be smaller, right? So 75% of the red balls are small. And only 30% of the green balls are small. If you do it like that, you can see there's a correlation. And all we're saying here is that these 2 numbers are different. 100%, that's all there is to the correlation. The 2 numbers are different. Over here, the 2 numbers are the same. In this urn, all the balls, regardless of color, tend to be small. About 75% each time are small. So, bottom line, a correlation is a relationship between 2 variables, and it says that they're different, right? So now let's think about what this means. What can you infer about a statement like smoking correlates with heart attacks? What can we infer from this statement? Option A, if you smoke, you will have a heart attack. Option B, if you smoke, you are more likely than not to have a heart attack. And option C, the typical person who smokes is more likely to have a heart attack than the typical person who doesn't smoke. All right, now if you think about the way multiple choice questions are often set up, you'll realize that the answer is C, right? I'm pushing you towards this answer. All of the extreme statements that I started out with, you can't infer. Really, you can't even infer anything particular about yourself. You only can make an inference about the typical person. To begin to do that instantiation syllogism and make an inference about an individual, you need to know more background information. So, smoking correlates with heart attacks just means that the typical person who smokes is more likely to have a heart attack than the typical person that doesn't smoke. Correlation is a relationship between 2 variables. We represent it with this kind of diagram. In fancy statistics world, a correlation is labeled R and is measured by a coefficient that's called Pearson's R, which is done on a scale of -1 to 1. And that just measures how strongly the 2 variables agree. If the number is positive, then changing one variable makes the other variable, it means that the other variable is likely to be high. If it's negative, then if one variable is high, the other one's likely to be low. So we have here the frequency of red balls in a population, right? On the right-hand side, the frequency of red balls in a small population in the population of small balls on the left-hand side, right? Oh, and I just said those two backward. I'm sorry. In any case, um, as you're looking at it, on the left is the large balls, right? And in this example, the large balls tend to be red. So the degree of the correlation, the strength of the correlation, is then mentioned in is then described by this distance here. Right, the distance between the two lines says how strong the correlation is. So in this context, we also have to talk about margin of error, right? This is the range around a given frequency where you can be sure that the actual number in the whole population is somewhere in that range. So if the frequency of red marbles in our sample is 55% and the margin of error is plus or minus 3%, we can be 95% sure that in the actual population, the number of red marbles is going to be somewhere between 52 and 58%. And I previously introduced rule of thumb margins of error. And I just want to emphasize this again. It's useful for interpreting political polling. If you have a sample of 1,000 individuals, that will typically give you a margin of error of plus or minus 3%, which is what most political surveys shoot for. This is assuming a whole bunch of things. Mostly that the sample is genuinely random, which is not something that you can actually safely assume for most political polling. That also assumes that the distribution of the trait is somewhere is somewhere in the middle, and you've got a very large population, more than 50,000 individuals. Let me just emphasize that again. As your population size gets larger, you can see in this chart, as the population size gets larger, the sample size you need to get a margin of error of plus or minus 3% gets larger, but it starts to level off. And by the time you get to 50,000, you don't need, it levels off basically completely. And adding more individuals at this point, making your sample larger in a genuinely random sample doesn't help you much. And this is just to emphasize that at a certain point, the size of the sample can't make up for whether or not it's random, right? So margin of error only includes mistakes that come from genuinely random samples. This is the limits of random sampling. It does not cover the mistakes from non-random samples or other problems with data gathering, which is where actually the problems with any kind of inductive generalization, but particularly statistics about people, come up. So we can think of our little correlation diagrams as involving a bit of margin of error, because we're moving from a sample to a population. So on top here, we imagine that there's a whole population, and we've got a sample that is some limited portion of that was chosen at random. We measure the random sample and then use that to make an estimate of the frequency in the whole population. That means that we have to put error bars around the frequency. We have to say plus or minus, say, 3%. And if we are measuring a correlation, we have to do this twice, right? A correlation involves 4 numbers, actually. If you're looking at the number of if you want to know if being large is correlated with being red in the population of balls in an urn, you need to know the 4 numbers in this. You need to know how many are large, how many are large and red, how many are red and not large, etc., right? And this involves two inductive generalizations. So we actually will wind up with two sets of error bars. I'm not going to go into detail about applying margins of error to correlations. The main thing I want to emphasize actually is just that people tend to infer the existence of a correlation when they don't actually know all the numbers they need to know to compare, to make two inductive generalizations, or to compare two variables. The other important thing to remember is that once you have actually managed to infer the existence of a correlation, you have not shown causation. The key here is that correlation is not causation. Let's just talk about that. The key is that correlation is symmetrical, but causation is not, just by its nature, right? So if X and Y are correlated, then Y and X are correlated. Where there's smoke, there's fire. That means smoke correlates with fire. That also means that fire correlates with smoke. The two, it's a symmetrical relationship. Causation doesn't work that way. If X causes Y, Y might not cause X. And if it did, you'd get some kind of runaway feedback loop, right? So fire causes smoke, but smoke does not cause fire. All right, so let's go back to the idea of heart attacks correlating with smoking. Suppose you've got 100 people, 30 of them smoke and 70 of them do not. Of the smokers, 3 have heart attacks, and of the non-smokers, 1 has a heart attack, say, over a lifetime. And I think this is more realistic than the example in the book, but that's just based on some quick Googling. And honestly, a lot of teaching critical thinking is just asking people to do basic fact checks, not in-depth research, so I'm comfortable with this. In any case, we can represent the correlation between smoking and not smoking, and heart attack and not heart attack, with a diagram like this. So I said we've got 100 people. We need to split up those 100 people over over the 4 parts of our diagram like this. 27 of them are smokers who do not have a heart attack. 3 of them are smokers who do have a heart attack. 69 of them are non-smokers who have a heart attack, and 1 of them is a non-smoker who has a heart attack. So we get this correlation diagram here, and as you can see, one side is higher than the other, so we know they're correlated. And we can say that smoking is correlated with heart attacks. Because correlation is symmetrical, unlike causation, we can flip this around. So we could do the same diagram again, and change the axes. Heart attack and no heart attack are now at the top. The correlation is still there. Correlate, right? We have to change our numbers. The columns add up to something different, but the basics remain the same, right? Smoking and heart attacks, smoking correlates with heart attacks correlate with smoking. So the correlation is symmetrical. Causation is not symmetrical. Smoking is the thing that's causing the heart attacks, and it doesn't work the other way around. So I just want to give a couple other examples that you can just hold in your mind. Think about the difference between correlation and causation, and then we'll talk about the exercises. So ashtrays correlate with lung cancer, right? That is just being around ashtrays. People, this example worked better when people used to smoke indoors, because you would go into a building, even like classroom buildings like ours, and there'd be ashtrays indoors. And my grandmother had an ashtray on her coffee table, because people smoked indoors all the time. And it's clear that being around ashtrays is strongly correlated with lung cancer. Um, but it's not the ashtrays that are causing the lung cancer, it's the cigarettes. The cigarette causes lung cancer. The cigarette also causes the ashtrays via the smoker, who has to purchase ashtrays to have a place to put their cigarettes. So whenever you have a correlation, there are multiple questions you want to ask. One is one of the items of the correlation causing the other? Does lung cancer cause ashtrays? Well, that doesn't even make sense. Does smoking, is there a third factor that causes both of them, right? So the exercises that you've got around moving from correlation to causation just ask you to speculate about what third factors might be involved, because that's the kind of inference you have to get used to making. All right, so here's another example that's in the text. Allergy symptoms correlate with each other. Sneezing and itchy eyes correlate with each other. But the sneezing doesn't cause the itchy eyes don't cause the sneezing. There's a third item that causes both, and that is the pollen. The last point is that correlation lets you predict. If you know two things are correlated, that means that they've happened together in the past, and you can make an inductive generalization that they will happen together in the future, right? It's not that strong a generalization because you don't understand why the correlation is happening, but it's the beginning of prediction. Causation, because it's asymmetrical, among other things, lets you change, right? So you can know two things are correlated if you know that a factor is correlated with a disease. Little red dots are correlated with measles. You can predict that someone who has little red dots has measles, but you can't change things. So you can't give someone measles by putting little red dots on their face. To really understand, to really manipulate the world, we have to know what causes what, right? And that's fundamentally, causation is a pragmatic idea. Causation is the scientific way of understanding how we can change the world. So ashtrays and lung cancer are correlated. The mutual cause is the cigarette. So that means that you cannot get rid of lung cancer by getting rid of ashtrays. You've got to get rid of the cigarette, right? And similarly, with the pollen example, you've got two symptoms. Affecting one of the symptoms won't affect the other. To actually get rid of the symptoms, you have to go to the underlying cause, the pollen, or the fact that the body's reacting to pollen, whatever. So again, correlation is a comparison. Correlation is a comparison between two statistics. Correlation is not causation. Correlation is symmetrical, causation is not. Correlation lets you predict, causation lets you change.